Good morning, class. The recording has started, and we shall continue from where we left off last week. Any questions about what we talked about last week? Not questions about the homework, but questions about the topics that we talked about last week. Any questions about signals? Any questions about SIG pending? Any questions about process creation? At least concerning the parts of it that we talked about so far, before we start. Nothing? Okay. I guess everyone is busy having their breakfast, drinking their tea, their coffee, or whatever you drink these days. So, big day today, process creation. This is an important day for you. It is an important day because starting from today, you will have the chance to do something that you weren't able to do in the past. You will have the opportunity, you will have the privilege even to develop programs that can do two things at the same time, that can do n things at the same time. So far, your programs always started from the beginning. They started from point A. They executed instructions, maybe a function inside a function. No, instructions, and they terminated. Starting from today, we will see how to start a process inside a process, which means your program will start as a single process, but it might branch out, dallanmak, branch out, and terminate as 5 processes, 10 processes, 20, 100 processes. And the beautiful part of it is that all of these processes are executed simultaneously. So you can have, for instance, a program that starts its execution and at the same time reads an MP3 file from your hard drive, sends it to the sound card in order to produce music from it, so play the MP3 card, have a second process in parallel that downloads the lyrics to that song and visualizes those lyrics. And you can have a third process that acts as a visualizer for the song. So with, weird graphics, etc., depending on the level of sound. So you can have 3 things happening at the same time. This wasn't possible before being introduced to multiple processes. But of course, as everything in life, whenever you have access to something new, and it gives you new privileges, new rights, new opportunities, new functionalities, this is very usually accompanied also by new problems. And make no mistake, there are big problems, new problems associated with this privilege, with the privilege of multi-process development. And that problem is, of course, synchronization, as well as communication. So when you have a process that branches out to 5, 10 processes, how do you communicate between those processes? Because we know that processes aren't supposed to touch each other's address spaces. And more importantly, how do you synchronize? How do you make one process wait for another process before continuing execution? How do you do that? And how do you do that when you have not 2 processes, but 12 processes, or 20, or 50? Those are big problems, but with very simple solutions. So, without further ado, let's look at process creation. Now, in the Windows world, and we don't care about the Windows world, there is only one function for creating a new process, and that is the spawn family of functions. But we don't care about that. We care about the world of Unix and POSIX, where we do the same thing, create new processes, but it is done in 2 steps. Now, we have already seen that there is a system library function that is used in order to execute commands in the previous slides, but you shouldn't use it. You shouldn't use it. Why? Security reasons. And also, it is very inefficient. You are asking the system library function to execute a command, and instead of creating a new process, it creates 2 new processes. One for the shell, and the shell creates a new process for the command that you want to execute. So why 2 processes instead of 1? For better control and for security, because system is also vulnerable towards the vulnerabilities of the shell. So for better control and for security, we do it on our own in 2 steps. How do you create a new process? Fork and exec. These 2 system calls. What do these system calls do? Fork makes a child process that is an exact copy of its parent process. It clones a process. The moment that you call fork, it starts cloning it. The moment that fork returns, you have 2 processes. Both of them at the same point. Both of them executing the instruction right after fork. We'll get to that. Exec, it causes a particular process, a process that called exec, to cease being an instance of one program and to instead become an instance of another program. Mikrofonu açık olan bir arkadaş var. Kapatsın lütfen. Thank you. So basically what exec does is very simple. The moment that you call exec and you tell it to execute some other program, it replaces all the code of the present program with the code of the program that you just called through exec. So fork clones the process into 2 copies. So you have the original and the new process. If this one calls now exec, it becomes a new process. That's the whole idea. So you started with 1 process and now you have 2 processes. Fork plus exec. Now, let's take a closer look. That's the whole idea. Now, here we have a nice visual example representing the idea behind fork. So you start the parent process, the original process, which is running the program A, whatever. A executes some instructions, and at some point calls fork. The moment that it calls fork, you have 2 branches. Now you have a second process. You started as a single branch, but now it continues as 2 branches. So you have 2 processes. The original one, which called fork, which we call the parent process, and the new process that was created after fork, the copy, which is called the child process. So you started with the parent, and now you have both the parent and the child process. Now, what is the child process executing? It is executing exactly the same things as the parent process. Exactly the same code. They are running the same program, same signals, same files, same everything. But it's a different process. It has its own memory space, the child. But they have the same program to execute. Now, at this point on, the parent, what does the parent do? The parent continues straight down. It may perform some other actions. It is free to do whatever it wants after fork. At some point, it might call wait. For what? In order to wait for the result of the child process. Now, when you call wait, the general idea, we will look at the details, but the general idea is that the parent process is blocked in the sense that it is taken from the queue of ready processes and placed to the queue of blocked processes. Waiting for what? Waiting for the child process to terminate. So the wait system call is used for waiting for one of your child processes to terminate. That's nice. And what does the child process do in the meantime? Well, the child process can do whatever it wants. It might perform some further actions after the return of fork. It might call exec and become an entirely new program. So it can become B instead of A, and eventually it will exit. Now, whatever it exits with, so exit 1, exit 2, return -1, that value will be returned to the parent process as the out through the wait system call. That's the general idea. Now we will look at the details. Any questions before we go further? Okay. Why create multiple instances of the same process? Well, as I said in the beginning, in order to do, well, for 2 reasons. 1, in order to be able to do multiple things at the same time. And 2, in order to be able to start new processes. I mean, we need to be able to start new processes. Otherwise, we will only have init. a single process? Well, we need a way to start new processes naturally. But more importantly, why would you call fork in the middle of a program? Well, you would call it in order to have two running branches that will do two things simultaneously. In this way, you can divide your tasks. For instance, last year, it was last year, I think, or the year before it, I don't remember anymore. There was a homework where they had a matrix to multiply or add, I don't remember. And it was given to a process, and that process was divided into multiple processes by fork in order to paralelleştirmek için, parallelize this task. So the process was divided into four sub-processes to four children, and each child process was responsible for processing 1/4 of the original matrix example. Or a more everyday example, a more professional example. For example, you can have a network server process, a network server such as a web server, a database server, a user server, and so on, that listens for incoming requests and creates one new child process to handle each request. For example, imagine the following. You open up your browser, I don't know, Firefox, Chrome, whatever you use, maybe links, who knows, and you try to connect to a website. Now, what do you do when you connect to a website? You enter a certain address, and the web server takes the address that you have entered, and it finds the file on the web server, and it sends you back the file. Now, this takes some time. This takes maybe, I don't know, maybe half a second, who knows, depending on the bandwidth, depending on the connection, depending on the strength of the server. But imagine that you have tens, hundreds, thousands of people making requests every second. So if the server handles each request as a single process, so I ask for a page, the server takes half a second to respond to me. That means for half a second, it cannot respond to anyone else. So that means it can only respond to two users in 1 second. That is awful. That is awful. So what do you do in its place? In its place, the moment that the request arrives to a server, you create a new process, which is much faster than half a second. You give the request to that new process, and the original parent process continues to listen to new requests. And so both the users are served with the pages that they have requested, and the server continues to listen to requests and respond to them by creating a new process for each new request. In this way, it can handle not two users, not two requests per second, but hundreds of requests per second. Any questions? Okay. If you ask this stuff after giving you the homework, I will not respond. Okay, so let's look at fork. Very simple system call. Very simple. No parameters. Fork doesn't get any parameters. So void, and it returns what? Now, this is tricky. Now, after fork returns, there are two processes. There is the original process that executed fork, and there is the child process that was created after the return of fork. So what does fork return? Does it return the same thing to both of them? No. Fork returns different things to the parent, different things to the child process. It returns the process ID of the child on success to the parent, if it is successful, or -1 on error. But in the successfully created child, it always returns 0. Why? Why does it return different things to the parent and to the child? Well, this way, we can check the return value of fork and determine whether the code is continuing to execute in the parent process or in the child process. That's how simple it is. And in case of an error, it is only returned to the parent, only to the parent process, not to the child. And why does it return 0 in the child process? Well, it turns 0 because 0 is not a valid process ID. It is not a valid process ID. So if it returns 0, fork, you can be 100% sure that this process is the child process that was just created by fork. No other option. Example. Here we have an example of using fork in order to duplicate, in order to clone, basically, a running program. So basically a process. So we have the standard input-output header, sys types, and of course the Unix standard header. We have the process ID, PIT type, in order to hold the process ID of the child process. We printf that the main program has a process ID of something something, which we access, of course, with the getPID system call. Then we call fork. Now, after fork returns, there are now two processes, the parent process and the child process. We check with an if, the value of child PIT. If it is different than 0, that means we are in the parent process, 100%. We printf that this is the parent process, here is the process ID, and whatever the value is returned in child PIT, that is the process ID of the child, assuming that it is not -1. So we can print it on screen right here. Else, well, when will else be executed? Well, if fork returns 0. When does fork return 0? It only returns 0 in the child process. So that means the if clause will be executed in the parent process and in the parent process only, whereas the else clause will be executed only in the child process. That's how simple and elegant this is. Any questions about it? Any questions about this example? Okay. You are very silent this morning, and this is worrying me. This is worrying me. Now, let's continue with our details. Let's continue with the details. Can you imagine what kind of different homeworks we can get out of this? There is a gazillion different homeworks that we can come up with using fork. We are going to have so much fun together. Now, the child process is created as an exact copy of its parent. How exact? I mean, what was in the parent? Now, imagine the parent process. What does it have? It is memory. It has the data segment, which contains global and static variables, both initialized and non-initialized. It contains the text segment, which contains the code of the program. It contains the heap for memory allocated through malloc, realloc, calloc. And it has the stack in order to hold the local variables and the function arguments and function return addresses. Now, all of this is copied to the memory space of the child process. All of it. Same code, same global variables, same local variables, same heap, same dynamically allocated, same everything. What about open files? Remember the open files? The parent process, let's say that it had opened 5 files, including the standard output, standard input, standard error, additional files. Whatever open files the parent process had, they are also open in the child process. Automatically, they are also open, and not only that, but they have exactly the same file descriptors. Now, remember the situation from past weeks? Process A and process B. Now, if process A is the parent process, then process B could very well be the child process. How do I know that? Because they have the exact same file descriptors, file descriptor number 2, pointing to the same file, which means they have the same offset. So if the child process writes something, the offset will move, and it will also move for the parent process. So, of course, the child process doesn't have to use the same files. It is free to close those files, open new files. Otherwise, it has the same standard input, same standard output, same standard error even as the parent process. So, long story short, the child process is an exact copy of its parent with only one exception. It has a different process ID. And that process ID is returned by fork to the parent. Everything else, the same between them. Everything else. Any questions? This stuff is important.
So when we do stuff with the child process, it becomes a different process completely, right?
It is already a different process. The moment
Well,
that fork returns, it is already a
obviously,
different process, but
obviously a different process, but in the sense of completely different process, like it doesn't have the same.
in order to execute different code, a different program,
Mhm.
well, in that case, you have to call exec. So they can be the same program with the same code. They can be executing different parts of the same program, but it is the same program. If you want the child process to become a different program, completely different program, so instead of being program A to become program B, C, or whatever, then they have to call exec. Otherwise, the child process, at best, it can execute only different parts of the same program. Just like in the previous example, for instance, the parent executed the if clause and the child executed the else clause, but they are still executing the same overall program. So if you want to become a new thing, a new program, you have to call exec. We will get to that.
Okay, thank you.
So let's take a closer look to fork. You're welcome. Now, here, for instance, another example from your book this time. Here we have the main method, the main function. Here we have two variables to hold the process IDs, and we have multiple forks. So what is happening here? So C2 originally has a value of 0. We call fork once. So we have two processes now. Now C1 will have the value of 0 in the child process and a positive value in the parent process. Now it says if C1 is 0, so if you're in the child process, call fork again. So the child branches out once again. And then it calls fork, but this fork is executed both in the children of the child and in the parent process. And then additionally, if C2 is strictly positive, so in the parent of the grandchildren, it calls fork again. So we have basically 4 forks. Now, normally I would have asked you at this point how many processes have been formed, but since you have access to the slides, I won't do that. So instead we are going to study it together here. So initially we start with a single process. Okay, we are here. We are just before the fork. We call fork, and now we have two processes. The parent process P1 and the child process P2. So this happens right after the first fork. And what is the value of C1? What is the value of C1 right here? Well, it will be strictly positive in the parent process, P1, and 0 in the child process. Now, then it says, if C1 is 0, call fork again. So in the child process, and only in the child process, we call fork again.
Sir, I didn't get why it was positive in P1.
I'm sorry, can you repeat your question, please?
You said it was strictly positive in the original process. Where does it say that?
It is strictly positive in the original process, in the parent process. Why? Because it will return the process ID of the child. A process ID cannot be negative.
Okay, makes sense. Yes.
There is no 0 for process ID. Process ID starts from 1. Always. And 1 is always in it. So you cannot have a 0 process ID or a -1 process ID. Okay.
I
So,
fell out, sorry.
okay. So we called fork. Now we have the parent process and the child process, P1 and P2. Now C1 will be a strictly positive value in the parent process equal to the process ID of the child, whatever it is. And in the child process, C1 will have the value of 0. And it says if it is 0, so if you're in the child process, call fork again. So it calls fork again. It executes this statement right here. So P2 is copied into P2 and P3, and it returns C2. Now C2 will be positive in the parent process P2, but it will be 0 in the grandchild, torun süreç, P3, the child of P2, who is a child of P1. Okay. Then it calls fork. Now fork will be executed in both of them, both in P1, P2, and P3, naturally. So P1 will be cloned into P1 and P4, P2 will be cloned into P2 and P5, P3 will be cloned into P3 and P6. And it additionally says if C2 is positive, so in the parent process, do what? Call fork once again. So if we call fork once again in the P2 and P5, then we will have P2 and P7 as well as P5 and P8. So in total, we have 8 processes after 4 forks. Any questions about this branching out procedure? Mr. Anil says, if the file is locked to the parent for writing, can the child process write to that file too? Ah, that's a good question. So if the parent has locked the file for writing and it clones this, and it gets cloned with fork, and now you have a child process as well, can it write to that file? As far as I know, let me get back to it. So here we have the file logs. So here, for instance, you have pointing to 73, which might be associated with a certain log. Well, in that case, without knowing for certain, my intuition is that they should be able to write there. They should be able to write. I'm not sure about this answer. I have to check it to make sure, but based on my knowledge, I would say yes, both the child and the parent should be able to write to that file. Because the log is associated, the log is kept in the inode table, the file logs, and it is associated with a single row of the open file table. And this single row, which also contains the offset, is common to both the parent and the child. For instance, 73 here. So my intuition is that, yes, the child process should be able to write to the locked file together with the parent. But as I said, I am not 100% sure. I have to check that. But file logs in general, in the POSIX world, they are what they say advisory logs. Yani mutlak kilitler değil arkadaşlar. Şey olarak algılamayın hani. Ya tamam ben bu dosyayı kilitledim, şimdi kimse dokunamaz ona. Yok, hiç öyle bir şey değil. Hiç öyle bir şey yok. What we mean by advisory log is the following. If you want to use logs in order to coordinate access to a file, all the processes accessing it must have agreed on this beforehand. So if, for instance, you have locked a file for writing, that doesn't stop any other process from opening it and writing to it. It will only stop the other processes if they also try to obtain a write log before accessing it. Let me repeat that. It's important. Just because you have locked a file for writing doesn't mean that you are the only process able to access it. Any other process that tries to open it and write to it will be able to open and write to it. It is not stopping it. It will only stop the processes that try to obtain the log before accessing the file. If they try to obtain the file, they will see that, this file has been already locked, so I cannot get the log, so I'm blocked. It will only stop them. That's why they are not absolute logs. They are just advisory logs. Is that clear? This is important. So do not be fooled by the name. It is a file log, so I locked it. Nobody can access it. No, it doesn't work that way. It will only stop the processes that try to obtain the log before accessing it. Arkadaşlar bu nokta net mi? Bak bu kilit konusu. Önemli çünkü.
Peki hocam yani genelde işlemler bu loka erişmeye çalışır mı yoksa direkt mi gider? Yani hangisi daha sıktır? Çünkü kitlemenin pek bir anlamı kalmıyor o zaman.
Salih Bey, kitlemenin çok güzel anlamı kalıyor. Kitleme ne işe yarıyor? Kilitleme bir dosyaya aynı zamanda birden fazla sürecin erişimini kısıtlamak için yarıyor. Şimdi diyelim ki sizin bir tane bir uygulamanız var. Paşa paşa gidiyorsunuz. Arkadaş diyorsun bak benim 2 tane sürecim var. Sen de bu dosyadan okuyacaksın, yazacaksın. Sen de okuyacaksın, yazacaksın. Ama ben yazarken sen yazma. Ne yapacaklar? Bunu işi garantiye almak için. İkisi de dosyaya yazmadan önce bir kilidi almaya çalışacaklar. Kilidi alan yazacak, alamayan tıkanacak, bekleyecek. Çok güzel çözüyor yani bu problemi. Ama derseniz ki hocam ben kilidi almak istiyorum ve hiçbir süreçte buna yazamasın. Öyle bir şey POSIX'te yok. Sen kilidi aldın mı? Tamam, kilit senin. Ama bir başka süreç var. Onun haberi yok. Orasının kilitli olduğunda ve umurunda da değil. Adam açıyor, güzel güzel okuyor, yazıyor, istediğini yapıyor oraya. Onu durdurmuyor. Kimi durduruyor? Ancak ve ancak oraya erişmeden önce kilidi almaya çalışanları durduruyor. Yani sen evin kapısını kilitledin ve diyorsun ki arkadaş bak herkes de bundan sonra şey var. Şimdi bunun örneğini vermek biraz zor ama evle biraz çünkü kötü bir örnek oluyor. Nasıl diyelim? Şöyle diyelim. Ha bak güzel örnek. Eve girişte anlaşıyorsunuz ve diyorsun ki bak eve girmeden önce kapıyı çalacaksın. İçeriden sana gel derlerse içeri gir. Gel demezlerse girme. Ve sen arkadaşınla anlaştın o şekilde ve öyle yapıyorsun. Kapıyı tıklatıyorsun. Gel sesi gelirse giriyorsun içeri. Gel sesi gelmezse içeri girmiyorsun. Ama bir tane de affedersiniz bir Denyo'nun biri geliyor. Ne kapı çalıyor ne bir şey. Dangur dungur içeri giriyor. O girer. Onu kimse durdurmuyor. Kapı çünkü kilitli değil. Sadece sizin bir anlaşmanız var arkadaşınızla. Bak kapıyı tıklat öyle gir içeri. Veya o arkadaş o anlaşmaya sadık kalırsa evet onu durduruyor bu durum. Kapıyı tıklatıyor. Ses gelmedi. Bekliyor orada. Çünkü sizin anlaşmanız o şekilde. Yani o yüzden advisory bir anlaşmaya bir sözleşmeye dayanıyor kilidin işlevi. Yoksa mutlak bir kilit değil, bir gerçek bir kilit değil yani. Kapı kilitli değil aslında. Yani isteyen girebiliyor. O mantıkla çalışıyor POSIX'teki kilitler. Umarım anlatabilmişimdir.
Gayet netti. Teşekkürler.
Rica ederim. Karanlık oldu ya. Okay. Process scheduling. Now, we called fork. The parent process was cloned. We now have two processes. But in the meantime, there is also a question. And Mr. Arnold says, so if we try to lock it first in all our processes, we can block the others. If you try to lock it first in all our processes, when you say our processes, what do you mean? The children of the parent process or the processes belonging to this user? The processes that I created in my program. Now, Mr. Arnold, let's imagine this. Now, you have a parent process. In this parent process, you lock a certain file. Now, that process has now the lock. Now, the lock is associated at this point with that file. Now, I don't want to make speculations at this point. I need to research this and answer you correctly, because right now I am speculating. Now, as I said, my intuition is that the child process should be able to access the file because they have only a single offset. But let me research this. I will get back to you on this. I will write a paper on. I will write an answer to Moodle and share it with you today. I'm taking a note for it. I will answer this today and share the file on Moodle. Now, process scheduling. You called fork. You have the parent process. You have the child process. Who is going to run after the fork? Fork returns. You now have two processes. Who is going to run? You have no idea. Nobody has any idea. There is no guarantee whatsoever about who is going to run. Maybe the parent will run. Maybe the child process will run. Maybe the child process will run all the way to the end and terminate before even the parent process gets a chance to execute. Or maybe the parent process will run all the way to the end, finish, and then the child process will get a chance to execute. Or maybe it will execute one instruction from the parent, one instruction from the child. We don't know. Never make an assumption about the order in which the parent and children processes are going to execute. Nobody knows. and nobody can guarantee anything. Process termination. There are two ways for a process to terminate, the normal way and the abnormal way. Now, the normal way is to call exit. At the moment that you call exit, of course, the process terminates. It doesn't matter if you call it in the main function. It doesn't matter if you call it inside a function within a function within a function. The moment that you call exit, the process terminates. When it terminates, certain things happen. Whatever you gave as a parameter to exit, it is returned to the process that started it. By convention, traditionally, nobody's forcing you, so it is only a convention. We return 0 on success, negative value in case of failure, and a strictly positive value, meaning that there is a weird situation. There is something special that has happened. Not successful, but it didn't fail, it didn't succeed, something else happened. So please try to conform to this convention. This convention is important. But as I said, it is only a convention. So if you want to return a negative value in case of success, nobody is stopping you. But that would be really weird. How can you read the value that has been returned by a process? For instance, when you execute a command. Well, when you execute a command on the shell, the return value of the last command executed is kept in this environmental variable, in this shell variable, the $! variable. So if you echo it, you will see, for instance, after executing ls, that ls has returned 0. Why? Because it was successful. If you try to ls a file that doesn't exist, you will see that ls has returned 1. It didn't fail, but it couldn't find the file either. When exit is executed, when you call exit, of course, the process terminates. And by termination, we mean that it will flush out all the standard input-output buffers. It will close all open files, open streams, everything. It will release all the locks held by the process. Basically, it cleans up after you. But of course, do not rely on exit. Do not rely on the exit function in order to clean up after you. Instead, you should be cleaning up after yourselves. What is even better is that you can use the @exit function from the standard library in order to register a handler. So basically a function, you give it the function address, and this is the function that would be called automatically the moment that you call exit. So you can have, for instance, all your cleanup methods inside this function func, which will be automatically called when you execute exit. And of course, there is the abnormal way. So not because you called exit, but because you received a signal. Now, there are many signals that can terminate a process. SIG_term, SIG_int, SIG_abort, SIG_buzz, SIG_segv, segmentation fault, the famous one. And by default, all of these signals, they terminate the target process. Now, some of them you can catch them, some of them you cannot catch them. For instance, SIG_int, yes, you can catch it. But segmentation fault, no. You cannot catch segmentation fault. You cannot postpone segmentation fault. The moment you receive it, game over. Or there is also the even more powerful kill signal, which immediately terminates things. In fact, there is also a nice picture about kill right here. I like this especially. So how the signal handling works. So if your browser Firefox freezes, what happens then? Well, in Windows, the operating system says, sir, would you please kill yourself in order to free some resources? And, well, it can either kill itself or not. You can get a blue screen. I mean, the entire system can crash. Anything can happen on Windows. In Unix, if the process receives the kill signal, there is nothing that can be done. That process is gone. It is gone. As simple as that. Now, here we have an interesting example now. Now, be careful with this example. Let's look at this example before taking a break. It's raining outside. Now, this example, we will have a fork, we will have a parent and a child process, but we will also have signals involved. We will do something weird. We will send signals from the, if I recall correctly, we will send them signals from the child process to the parent process. And the parent process, well, let's see what happens. Let's see what happens. Now, this is the handler method. What does it do? It receives, of course, always a single parameter, the signal number, and it checks that signal number. If it is signal user 1, it simply prints on screen the catcher called sig user 1. If it is sig user 2, it prints the catcher called sig user 2, and by default it prints the catcher called an unexpected signal. Of course, remember that it is a bad idea to call printf inside the handler. So this is only for the sake of the example. Let's look at the main method. Now, the main method, we have a variable to hold the signal mask. We have the struct sig action to hold the action for the handling, and we have the time. Okay. We call fork in the parent process. Now, as soon as fork returns, there are two processes, the child and the parent. So it checks whether fork returns 0. So that means this if clause will be executed in the child or in the parent. Since it returns 0, that means it will be executed in the child process only. And what does the child do? The child first sleeps for 10 seconds. Okay, so it goes from the queue of ready processes to the queue of blocked processes for 10 seconds. Then it returns to the queue of ready processes and prints on screen the child is sending the sig user 2 signal. How do you send the signal from one process to the other? Very easy. You use the kill system call. First parameter, the process to which we are going to send the signal. So it is sending it to the parent process, get parent process ID, and it is sending signal user 2. After sending it, the child process sleeps for 5 more seconds. So from the ready queue goes to the blocked queue. Then it returns from the blocked queue to the ready queue. Then it sends sig user 1 and exits with a normal 0. Okay, so the child basically sleeps a little and sends 2 signals to the parent. Fine. What does the parent do in the meantime? Now, the parent does some interesting things. First, it initializes the mask inside sig action to 0, so it doesn't want any signals blocked while the handler is executing. It sets the flag to 0. It sets the handler inside struct sig action to the catcher function that we saw in the previous slide. And then it has this interesting if-else-if clause. It first calls sig action with sig user 1. So basically it says it registers the catcher function for sig user 1. So if this process receives sig user 1, it is supposed to now execute the catcher function. Okay. So if it returns something other than 0, it means sig action failed, so parror will be executed. Otherwise, if it is different than 0, if it is 0, in that case, this clause will not be executed. It will switch to else if, and it will execute sig action again, which means sig user 2. For sig user 2, we also register the same catcher. Okay, so that means it also executes this. And if it is successful, that means this else if will not get executed and it will switch to else. Okay, so what have we done so far when we reach this point? We have registered the catcher function for sig user 1, and we have registered it for sig user 2. For whom? For the parent process. Okay, then what? Then we have a mask here, a signal mask, sig set. We fill it, which means we set as on all of the signals in it. And we only remove from inside it sig user 1. So all the signals inside this mask are set except for sig user 1. We take the time, we write it into the variable t, okay. And then the parent says, the parent is going to wait for the child to send sig user 1. And then it calls sig suspend using this mask. Now, what does this mask contain? This mask contains all the signals except, we have the del here, except for sig user 1. So that means this process is going to go to sleep waiting for any signal. Waiting for which signal? It will go to sleep waiting for any signal but sig user 1. It will go to sleep waiting for what? Sig user 1? Sig user 1. Everything else will be blocked in the meantime. The moment that we call sig suspend, all the signals that are set inside it are blocked, and we are waiting for sig user 1. Okay. And when will it continue? It will continue where sig user 1 is sent. Okay. And what happens when it returns? What happens when it wakes up from its sleep? It prints F, it only that the sig suspend is over at this particular time. Now, what do we expect to happen? The parent goes to sleep by calling sig suspend. It basically blocks itself, waiting for sig user 1. What does the child do? The child, in the meantime, it sleeps for a while. Then it sends sig user 2, but sig user 2 is blocked, so it will not be delivered to the parent process because sig suspend automatically blocked all the signals that are set inside this mask. Then it sends sig user 1, which will definitely wake up the parent process from its sig suspend sleep. But when it is woken up, it will also be delivered all the signals that were pending. So it will also receive sig user 2. Arkadaşlar bir hayli karmaşık bir örnek. Let's look at the output. The parent is waiting for the child to send sig user 1 at this particular time. The child is sending sig user 2, but it is blocked, so it is not delivered to the parent process. Who blocked it? The parent blocked it the moment that it called sig suspend. Why? Because that signal, sig user 2, it is set inside sig set, inside this mask. The only signal that is not set is sig user 1. So that means all the signals except sig user 1 will be blocked during the sleep of parent process, except for sig user 1. So sig user 2 is not delivered. It sends sig user 1, which of course is received, by the process, the parent process. But at this point you might say, İdo hocam, neden önce sig user 1 kod yazmıyor? That's a good question. Why do you think?
Might be because of the stack. I don't know.
Because of?
The stack. Maybe whole
Sesiniz kesik kesik geliyor Gonca Hanım.
in a stack. My microphone is a bit far. Maybe wait, pending processes are stored in the stack. I don't know. It's just a guess.
I don't know. They are not kept in a stack. There is no such structure, as far as I know, for storing the signals. But this is the standard output now. It is not standard error. So there is basically no guarantee in the order of the messages. So imagine it receives sig user 1. It gets out of its sleep. It wakes up from its sleep. Now at that point, which signals are supposed to be delivered to it? Of course, the signal that woke it up, sig user 1, and of course, sig user 2. Now, sig user 2 was already pending, and sig user 1 just arrived. So in which order are these going to be delivered to the process? Should the kernel deliver first the signal that was pending, or should it deliver first the signal that woke up this process? No guarantee. There is no guarantee. If you execute the same program at your place, you might receive a different output. Your output might be sig user 1 before sig user 2. So these two messages might be even interchanged. The bottom line is that the moment that it returned from sig suspend, so it woke up, both of those signals were delivered to the process. So both of them were caught in the catcher function, for which the parent printed catcher code sig user 1 and catcher code sig user 2. But there is no guarantee in which order they are going to be delivered. So that was the objective of this example. Do not make any assumptions on the order of delivery of the signals. The only thing that you have for sure here is that the moment that you call sig suspend, you can be certain that you will sleep until sig user 1 arrives. And what about the sleep calls? What about the sleep calls? What would happen if we remove them? What would happen if we removed these sleeps? The sleep for 10 seconds and the sleep for 5 seconds. Any guesses? Well, basically, this is what would happen. This is what could happen. If you remove these sleep methods, what could happen is the following. After fork returns, maybe, just maybe, these instructions inside the if clause would be executed before the parent process got a chance to execute. So that means the child process would execute these instructions. So it would send the signal to, send the signal user 2, send the signal user 1, and then terminate. And then, of course, they are sent to whom? To the parent process. But the parent process didn't yet get a chance to register the catcher function. So there is no handler for them. And what is the default disposition for signal user 1 and signal user 2? The default reaction is to do nothing. So the parent process would do nothing at this point, the default reaction. Then it would register the catcher function. Then it would go to sleep waiting for sig user 1. But since the child process has already exited, no one would send it the sig user 1 signal, and the parent process would remain suspended indefinitely. See how great a difference makes just a sleep invocation at the proper place, at the proper time? But of course, using sleep is attractive in order to achieve synchronization between processes. But it is also a bad idea. Normally, we try to avoid as much as we can to use sleep because why? Because very simply, it means that the process does nothing. It is wasted time. Sleeping is wasted time. Ideally, we should have a solution for making sure that the child sends the signals only after the parent process has already registered the handling function. That would be an ideal solution. Now, any questions about this example? Okay, class, in that case, let's take a break for 5 minutes. It's 9:27 and we will continue at 9:32.